So let me do my talk. It's called an Introduction to Metal Additive Manufacturing. And I've sort of started off assuming you're not very familiar with the technology. So if you have, just, you can zone out or do something on your phone for 10 minutes. And when I say, or turn it off, yes. I'll try and make this interesting. So these are the 5 things we're going to talk about today. A quick introduction to our company. Just because I always like to start with that, because it'll lead into why we're doing metal now, and how it's been the culmination of something we started in '94. And then I'm going to talk about introduction to additive. This has been done so many ways. I try and put a different spin on it, so I hope you like that. And then I'll be talking about drivers for additive manufacturing. Drivers for, sorry, that was supposed to be funny. That was not intended. And then we're going to really spend the bulk of the talk, the last 30 minutes or so, 35 minutes, on deep diving into metal. And also I want to end with some of the resources that are available in Arizona. We're really trying to get the Arizona additive community together and do a bunch of things. So I'll talk about that in the end. So let's get started. A quick introduction to our company, only 3 or maybe 4 slides. We do 3 things. So if you've worked with us on our 3D printing services, you may not know that we also do simulation and so on. So the open house is a good opportunity for us to show everyone that we actually do 3 things, and they are simulation, product development, and manufacturing, and additive is a big component of that, as I'll talk about in a minute. And in each of these 3 areas, we do sales, we offer services, we do R&D, government funded typically, SBIR programs, we do some training and consulting. So it's a very interesting place to be, and you could find yourself wearing any of these hats on any given day. So if you like that, we're a nice place. It's hard to focus on the other side, other hand rather. So let's go into the next slide. We were founded 22 years ago, 94. Any historical event anybody knows? 94, what happened in 94? What? Yes, thank you. I was going to say it was the end of Nirvana. They broke up in '94 because Kurt Cobain. Anyway, so it was a big band for me, so I like to point that out. Sad year for me. But this company was founded, so on the other hand. So we're about 82 employees now, and we've served over 1,700 customers. We also, and the reason I'm putting this out here is really this is one of the emphasis of our metal 3D printer. We do R&D. We've won 13 SBIRs since '99, and most recently we won an America Makes Award, which is an institution, a federally funded institution to do research in additive. Especially with metal, one of our areas of focus is not to become a service player in the near term, but to become an R&D player with metal additive. So that's why I bring this point up. We do have offices in 5 states: Arizona, Southern California, Colorado, New Mexico, and Utah. But most of us, about 50 to 60 of us, sit here on this campus. And those are the 60 of us. And I normally ask, no, never mind. Find me in there. But this is our timeline. And when I came to PADT, I didn't attend an open house, but I got a tour, and I sort of fell in love with the company. And then 1 year later, I joined PADT. And the big part of this is because we have, one of the elements is we have 5 different 3D printing technologies. So under one roof, which is kind of amazing when you think about it, especially if you're like me and you're wide-eyed and you want to get involved with 3D printing somehow. This is one of the rare places that offers all 5 of these. We got our first, and you will see these machines as you walk through today. The bulk of our talk will be on our latest entrant, metal, but keep an eye out for stereolithography. That was our first machine, and also the first patented 3D printing technology in 84 or 84. 10 years later, we got our first machine when the company was founded. We then grew to add FDM, Then we added SLS, Polyjet in 2009, and Metal most recently a couple of months ago we finally got it installed, and a month ago we got it up and running. So we're relatively new players to Metal in that sense, but we've been adding technologies, and as the technology has been getting replaced with newer ones, we've been adding those as well. So you'll see the ProJet 6000, you'll see the Fortis 450, you'll see the you might see the SLS. I think we closed that off, but you will definitely see the objects, and you will get to see the MLab Qsing R right after this talk is over. So that was a quick introduction. There's of course the whole point of this open house is to introduce the company. So as you walk through and talk to everyone, you'll get a much better flavor. So introduction to AM, and again, this is where you can zone out if you're familiar with all of this, and I'll say zone back in at some point. But this, the classical, or the way that one of the ways you can define it is in contrast to subtractive. Conventional manufacturing involves a feedstock, us removing material to get a product. In additive, we start off with the material. We do layer by layer deposition in a sort of Zen-like way. We're only putting material where it's needed, which is kind of cool, and then we end up with the product. So this is conventional, subtractive, removing material, 3D printing, additive, adding material. But the better way that I like to think about it is the funnel cake at the State Fair, right? That is additive manufacturing as well, because and the reason I bring this up because this will feed into my next slide. I want to make a point here that there are so many different technologies, and 5 of them here, but 25, 30 technologies out there, with more coming online. But in my mind, they boil down to this simple concept that you have some raw material, you have some process that takes that raw material and applies heat, or in this case, you have a funnel and a nozzle with a specific diameter, and you make this raw material batter, and then you have heat, you have a plate, and all of that together is what we'll call the process. So you have a raw material, you have process, and then you get a final product. And as you can see, this is such a complicated design that if I was to give you this design, it would be very hard to make except through an additive method. So people also give the example of the pyramids of Giza as being additive manufacturing because they put blocks together. But I like this raw material process and product idea. And the reason I put that slide across is because you can even think of additive processes in the same way. We have raw materials that are either powder, and this is the SLS, the metal that you will see on your tour at PADT. Liquid, the stereolithography has a liquid resin. Our inkjet or our polyjet printers have liquid resins. And then we have filaments or wires, which are the FDM, or the fused deposition modeling, the MakerBots, the the cubes and so on, and definitely all the Stratasys systems that you will see today. And finally, the one thing that we don't have here is the sheet-based additive, where you start off with sheet-like materials. And then the idea is you take each of these materials and you apply some process to them. So with powder, what you will see today is laser-based melting of metal powder, but one can also have electron beam. Our friends about 5 miles from here have Titan Industries and LAI have an electron beam machine, and then there's binder jetting, another way to put in binder into raw material, into the powder, and bind it together. And also you can deposit powder with a laser, and this is called directed energy deposition. So that idea of taking a powder and applying some heat or some binder was what I thought was elegant, and is simplifying or simplifies the classification. With liquid, we can have lasers, we can have DLP type light projection, we can have material jetting. At PADT, we have the laser polymerization with SLA. We have material jetting with the polyjet, and then a UV light comes and cures it. With the filament, we can have fused deposition of polymeric materials. We can also have metals and an electron beam. Again, this borrows the same idea of depositing material. And finally, with sheets, one can do ultrasonic bonding or laser lamination. Not technologies that we have here, but that are available out there. So, I actually was thinking of printing a bingo sheet, and every time you see a technology over here, you can sort of say, check that off. But we have 5 of these combinations that you will see today on your tour. One of the things is that if you're in this industry, every year a gentleman and their team, his name is Wohlers. He started publishing an annual report about 20 odd years ago. And there's lots of charts, the state of the industry, but this is the one that I like the most. And this goes back to 2003 all the way to 2014. And what it essentially is the percentage of revenue in additive that is coming from functional part production as opposed to models or prototypes. Right? And thinking back to 2003, it was about 4%, and today we're about 43%, or 2 years ago we're about 43%. So it's a good bet that at 2016, about half of the revenue that we are generating in additive is going towards something that's going to end up on a plane, on a car, on a motorbike, or in a medical implant, or whatever. And that includes everything, the materials, the technology, the service, right? Now you have analysis, you need much more stringent part requirements, the certification. So that is a very important thing to keep in mind. The bulk of this growth is, especially in the recent years, is driven by metal. People say 2012 was sort of the tipping point when additive really started taking off, and this is one reason why. There are real examples. I'm only looking at, I think I have some medical examples after this, but if we look at aerospace and medical, that are the 2 leading industry leaders in this space, this is a picture of just FDM, which, can I have a show of hands if you have used a 3D printer? Okay, and if you have seen one work, or, yeah, okay. So the FDM is a simple machine, simple concept. It's simplified in the MakerBot system, but these are examples of people using that technology, the FDM technology with the filament, and we have lots of these examples to essentially make parts that end up on aircraft or on rockets, which is quite amazing. If you think back 5 years ago, this was not the norm. Maybe a few companies were doing it, the Lockheed Martins and so forth, but it definitely was not across the board like we're seeing now today, where electric wire covers, ducting, both at ULA and a company called Orbis. Anytime there's some complicated ductwork design involved, they go with FDM. Another toroid housing for some electronics, instead of manufacturing them, they decided to 3D print them instead of manufacturing them conventionally with injection molding. And also these gimbal eyes on UAVs, and here shown on a helicopter, again also done with 3D printing. Airbus has a good example of where they had an old part that ran out of, they needed to replace these safety belt holders on their A310s, and they decided to 3D print it instead of retooling the supplier. The original supplier had gone out of business. They had made these parts 30 years ago. So just great examples and real examples that lend credence to the slide I showed previously. These are some examples that are leading up to that revenue growth in functional part production. This is polymers. On the next slide, I have examples of metal parts, an exhaust gas sensor, very complex designs, and we'll talk about some of this when we dig deeper into metals. Brackets, a one-piece sensor, consolidated, a bracket from Honeywell, a fuel nozzle, GE Aviation, and a fuel nozzle for space launch from NASA Marshall. So again, all functional parts, and we'll see a little later what situations justify using 3D printing for parts like this. One thing you can see visually is just that they have very complex designs. So that is definitely one of the big drivers. There's all these market graphs that I put in here, but I'm just going to move past them. So forgive me for that. I don't want to bore you with too much graph. But the one point I do want to make is that was aerospace. The other big industry is medicine. And most people who follow the hype curves and for what it's worth, suggests that that's where the future growth is coming for additive. This could be in implants with metal. It could be bioprinting, using 3D printing for organic materials. And I like to sort of say that's sort of the next big thing in additive that's an R&D area now, and maybe 5-10 years. What metals was maybe 5-10 years ago is where we will be in 5-10 years with bioprinting. So that's something to keep an eye on. Finally, just the way, I didn't mention this, but the FAA has approved many of those parts I showed for aerospace. The FDA has approved about 70 plus devices, now closer to 100, for use that have been 3D printed. Again, most of them, 68% of them, had some kind of complex design. They end up mostly as orthopedic implants, hip implants, knee implants, and so on. Surgical guides that are temporarily used or inserted into the body, and 7% of it is dental. Most of the technology involves powder bed fusion, which we will see when we go look at our metal machine. So that was sort of my introduction to additive. Now I wanna quickly go through the drivers. So if you're very familiar with the technology, you can still stay zoned out. Otherwise, now is a good time to come back. So what I mean by drivers is why would you choose to go with 3D printing for a particular application? And broadly speaking, there are 5 drivers that would say, let's stop doing things the way we are or were doing it, and let's evaluate if we should be doing this with 3D printing instead, or additive manufacturing instead. Both terms are used equivalently. The first one is rapid prototyping, and which is and tooling, which I'm bundling here together. It's the most near-term gains to be had in many companies is by not only doing prototypes but also expanding it to tooling. The second one is what I hinted at when we looked at that metals page, the promise of design freedom. The third one is, in many cases, you can reduce your lead time. The fourth one is cost reduction in some cases, and finally, new applications that are on the horizon. So I'll go through each one of these with some examples. The first one is rapid prototyping, and this is the genesis application of this technology, going back to the late 80s through the 90s, and even today. A lot of what we do is used for prototypes, either for, these are all Lockheed's examples, wind tunnel models, display models, but even mock-ups and fit tests to sort of get a sense of how things will work, and because this allows you to iterate quickly. We could print something like that on the order of several hours, maybe have it ready in a day for testing. If we don't like it, we can modify it and get it back in a couple of days. So the quick iteration makes this ideal for mock-ups, fit tests, and testing in that sense. But you can also use this a lot for tooling. Drill jigs is one example, microvane tooling here, and even layup tools for composites. And when you go to the demo room up front, which is our prettiest room on campus, so I suggest you leave it for the end, so you leave with a positive feeling. But the demo room has lots of examples of tooling. And this is really, a lot of people that got this machine or got this technology for prototyping, that was like, wow, we can do so much with tooling. And a lot of this is organically generated from the shop floor because they are right at the place where value is added. So this is a very exciting field for this technology right now, especially on the polymers. A big growth area is tooling right now. The second one is this idea of design freedom. So the first one was, tooling and prototyping exploits really the ability to make low volume parts quickly and deliver them at the point of use. But another concept that is independent of that is the ability to make structures that have complex designs that you wouldn't be able to make otherwise. And if you think back to that funnel cake example, to start off with a block of cake and chip away at it to make that would be much harder. But such complex designs are often easier with additive, and additive imposes its own set of constraints Supports are a big one. Always, it is freedom does not come free. So this is a classic example. But I digress, and I'll talk about supports a little later. But these are some examples of parts. This is a UAV wing done on Stratasys equipment with FDM technology on an unmanned aerial vehicle or a drone. This is again that fuel nozzle and another fuel nozzle. This is very complex geometries that would require multiple parts to be assembled together that are essentially printed as one part. Because in additive technologies, you can do that. The second idea, which is very exciting in the aerospace industry, is the ability to finally unlock our software to give us the best solution possible, something that we do here as well. So we have a few simulation tables and some examples. I think we broke this recently, but Mario stepped out as soon as he saw this picture, because I think it broke while he had it in here. So, but this idea, we've had the software to say, that's the bracket that I want to design, but now I say I'm gonna pin it here and here or something. I'm gonna apply a load. The software can solve for it and tell me exactly where I need to put material. So topology optimization is the term that we use for it. And now we can actually print a part like this with all these openings here that reduce weight, and essentially we don't have material where we don't need it, where it's not really load bearing. So that idea has been exploited here by Airbus to simplify or to reduce the weight on a bracket by 30%. This is a seat belt buckle. It was a 55% weight reduction, and if you multiply that by the number of seat belts on an aircraft, the number of miles it flies, the savings are on the order of many $1 million over the lifetime of the aircraft, even after you account for the fact that this would probably cost more to manufacture in the first place. And some other examples of an exhaust sensor, again, not a weight argument, but just the sheer complexity of being able to isolate 6 different streams of exhaust for analysis in the sensor module is another example that really you would have to weld and do a lot of complicated assembly work to get this to work without additive. And finally, that notion of design freedom, I touched upon it, also applies to not needing to assemble parts. So this waveguide was for 77 parts if you include the little fasteners and the different parts that had to be assembled together. So you have the assembly time, you have the fact that you can have a failure initiating at these interfaces. And a metal company called Renishaw took that same design and essentially printed it in one part, lighter weight, fewer components. GE took down 20-part sensor housing down to 1. This is an FAA approved component. Airbus has an example of a fuel assembly where you have flow on the outside and on the inside, and they took down 10 parts to 1. ULA has this duct example where they had 140 parts in their ducts that used to cool their electronics, and they dropped it down to 6. These are amazing examples of sort of a second order design freedom now, where you can say, previously I couldn't put it all together because I was constrained by manufacturing. Now you can, and you can reduce the assembly effort and the risks associated with that and the cost associated with that. The third point is lead time reduction, and this is one of the reasons the DoD, the Navy, the Army are very interested in this. We have C-130s and a fleet of aircraft and ships that need part replacement. This is the way from a 2011 Air Force, the US Air Force had released a document where they sort of looked at in great detail how would they source parts. You don't want to create too large of an inventory, but when you have critical items with complex supply chains, you want to minimize the risk by having multiple suppliers. All this is adding cost and logistical management and retooling up every time you need a trigger makes this really complicated. And then we have aircraft and weapon systems that are mission incapable awaiting parts, or MICAP. and they monitor that. And there was a research call last year to sort of look at how we can start with polymeric materials to bring that at point of use. This is one of the sort of the vision ideas from Deloitte, which sort of shows 3D printers on an aircraft carrier, and you know, assuming we could get there. And the Navy is actually evaluating 3D printers on ships and how to deal with the dynamics of the ship and still get a good part. And this is exactly what they have done. I think they installed this 2013. Closer to home, Raytheon in Tucson is actually evaluating 3D printing missiles, including embedded electronics. And I think they've already shown they can do 80% of their missile now can be 3D printed. They're actually working on a project to see if they can 3D print and assemble this seeker at the head of the missile in an automated manner. So a lot of exciting work going on, and the idea again is you reduce the supplier complexity, you bring the printer to the point of use, and reduce that distance, and especially for the DoD, it's a very exciting field. Also in the development cycle, SpaceX has this example of having printed this Draco thruster that is about yay big, from concept drawing to hot fire in 100 days, which I believe is unheard of. I don't know what is a good period, but it does sound quite amazing that they developed this thruster and brought it to testing. It's made of Inconel. It wasn't a powder-based laser system like the one we're going to see, only much larger machine than we have. And that was one example of how they reduced development times. I talked about the Airbus example for the replacement part. Within a week, they had a part in hand from old drawings that were made 30 years ago. And also, you know, we can use additive technologies for repair. Instead of you know, tossing out this turbine blade on-site repair with some finishing, this can be put back in action and reduce the mean time to repair on these kinds of metal structures. Fourth is cost reduction, and this is the classic cost curve, cost versus volume. Fewer units, conventional manufacturing gets more expensive, and as we scale in volume, we get the advantages of scale, and our per unit cost reduces. And an additive is somewhat of a flat curve. This is not strictly true, but it's pretty flat. Reason for that being because of that layer by layer, whether you're making 100 funnel cakes or one, you still need to have that process advantage. You still require that much process effort on each part. So the theory is that for all parts there exists some break-even point where additive becomes cost competitive to the left, but conventional manufacturing is cost competitive on the right. And some extreme examples are, I believe there are about 10 million hearing aids that are 3D printed. If you get one today, it's very likely it was 3D printed because each one is unique. So in most cases, hearing aids, braces, implants, because of the customization capability, and conventional manufacturing loses out additive gains. On the other extreme, ducks and rubber duckies and wafers would probably never get to, or this cup over here would not be able to match that just because of the volumes driving down costs. But the real interesting problem is what lies in between and how that varies. So a lot of companies are looking at this. They have systems and software to go and evaluate this, especially in metal, which can be quite expensive. So it has to be justified well. And of course, this is complicated because you may have design freedom enabling consolidation. So and you have to look at the lifespan of that part and what it offers during manufacturing, labor cost reductions, maybe supply chain simplification costs. So it's a challenging problem to find out if it is worthwhile doing. Finally, new applications, 3D printed electronics, space construction, armor and exoskeleton, actually building these space frames up in space, and bioprinting are all new ways we can use additive manufacturing. So this is sort of my 5 reasons why you would want to look at this technology that you cannot do in other ways. And now, this took longer than I expected, so I'm sorry about that, but now we're going to talk about metal additive. I should have taken those drivers out in hindsight, but I hope it was useful. These slides will be made available if you ask me for them. We're not going to put them public because I don't have some of the rights on the images here. Let's talk about metal 3D printing, and I want to start by there has been one more entrant, at least one more recent entrant, but these are the three that are commercially available out there. And I'll try and do justice to all three of them. The first one is powder bed fusion. That's the idea of having a bed of metal powder and using some heat source to melt that powder. And we will be looking at one of these, which is the laser-based fusion technologies. And I'll talk about that in a little more detail, and we will see it firsthand. So I'm going to not spend too much time on that right now. But that is number one. It is the most commonly used metal technology. It has the biggest slice of the pie. And there are many names for it: selective laser melting, direct metal laser melting, direct metal laser sintering, powder bed fusion. I like powder bed fusion. Powder bed fusion makes sense. And this is one idea, is use a laser to do that. The other idea is use an electron beam to do that. You have an electron beam, you have these magnetic lenses that align the beam, and essentially the same idea that it does share is the notion of a powder that you're then melting layer by layer. So very similar, they're sort of cousins with just different sources, a laser and an electron beam. Secondly, we have directed energy deposition. This is the idea where you don't really have your metal or your raw materials sitting at the bottom, but you're actually shooting it, sort of like welding, where you're providing the material at the source where it's needed. So this is done in two ways. One is with a laser system, and you have powder being delivered at that point. We saw one picture of that before. So if this is your part, you align everything perfectly, the surface, the laser beam, and the powder, and you get that to work together, and you can make parts like this. The same idea you can apply to a wire and an electron beam, and again get it to all conform at a perfect spot, and build up your part like that while you move the platform underneath it. The third technique is to use powder bed binder jetting. What it does share with this is the notion of a bed of powder. What it doesn't share is you're not using a heat source, you're using a binder. So you have these binder coming out of these droplets, and you deposit them exactly where you want your part on that particular layer. So everywhere where the binder falls, it essentially glues the particles together. You then take it out, you can brush off all the powder, and you go put it in an oven, get rid of the binder, and then you can infiltrate it with another metal that comes in and wicks into the rest of the part. So that is binder jetting, another way to make metal parts. And they are very different, and they all have their place to play. And this can become a controversial slide, which is why I make it as verbose, just to be fair to all four technologies. And I'm not going to read through this, but my point is that broadly speaking, laser-based systems are good when you want strong properties, you want to have access to a wide range of materials, you want to make typically parts on the order of 10s, 20 inches. That Draco thruster is probably the largest you would go to, though people are pushing the limits. But we're talking about the ranges of inches, maybe touching a foot, in extreme cases. Same thing with electron beam. Great properties, not as much options in materials, but a similar, slightly smaller build size, but we're talking about that domain as well. Today they're very well known for titanium 6-4. They also offer cobalt chrome, and I think more recently they've added Inconel. Whereas with lasers we have many more material options to play with. Laser systems on the downside do need a lot of support structures, both for stress relief and to a second order for thermal dissipation. Electron beams primarily needed for thermal dissipation, not so much for stress relief. you typically get slightly lower residual stresses on electron beams. And so these two are fairly comparable in that sense. The deposition processes, be they electron beam with wire or powder with laser, are great at making big parts. And you can see this part over here, and relative to a human scale. If you want to make something on the order of feet, this technology is great. The downside is you can't, as you would expect, you can't resolve very fine features. You have this sort of very strong layer by layer effect that you have to do some kind of post-processing, some machining on later on. But depositing chunks of material very fast, this technology is great. And finally, binder jetting, because it's occurring at such a low temperature point, you can make parts and without the need for supports. This is one of the only true support-free techniques that we have. It's affordable to make parts compared to the other technologies, lower price point to make these. Properties, on the other hand, are not as good. As you can imagine, we have this binder, we're getting rid of it, we're infiltrating it. We could have two-phase materials, but great for making sand castings, great for making metal prototypes, functional prototypes, fast and in an affordable manner. Yes?
You say a couple of these have strong properties. Do they come close to starting with a billet and using a subtractive part, the strength of those?
They do, and I have about 3 slides on that, so I'll touch upon that. But that was one of the biggest advances in metal 3D printing, that we finally got parts that had comparable properties. And I have some data on that I'll show you in a sec. But yes, short answer is for all these 3 technologies, not so much for the binder, parts have that quality now. There are questions around fatigue performance and some other things that I'll show you. I'm getting ahead of myself, but very good question. And that is also the area that we are most interested in at PADT, in participating in that research question. So that was the end of my discussion on other technologies. So from here on out, I'm only talking about laser-based systems. That's what we have here. That's the one I'm most familiar with. But we definitely have electron beam 5 miles away from here with a company called Titan Industries. And they are coming here at 6 o'clock. So definitely we have access to this in the valley. These two are a little harder to get, but at least these 2 systems we do have right here within a 5-mile radius. So everything now on is laser-based system. So this is really a laser-based system, and what you're seeing on the right-hand side is a dual laser system, and it's actually melting the powder. But I want to draw your attention to the left for a minute, and there are 4 components of this process. The first is the laser, as you can imagine, and it has an XY through the mirrors in the galvo in the laser. Then we also have powder, and we have inert gas. This must be done in an inert atmosphere, typically nitrogen, aluminum and titanium argon is the recommendation. And finally, we have a coater blade, which sounds trivial, but is very important when you realize that our layers are 25, 30 micron thick. So we want this coater blade to come across this and deposit a 25 micron layer. So its setup, the design is very important. So while there are other components, of course, in this system, these are the 4 components that typically you have to get right to get a good part out, as a user. If we dig a layer deeper and actually look into what is happening in this process, there's a group at Lawrence Livermore that actually does simulation, since there's no other way to really see what is happening when the laser is melting these particles. But the particles start off as metal particles that are almost perfectly spherical. At least when you look at them, they look really highly spherical in nature. They typically have about 20 to 60 micron diameter, which is a thou to 2.5 thou in inches diameter, so really, really tiny. And these particles are being, they have a normal distribution typically, and we're using some source, in this case a laser or an electron beam, to actually melt these particles. That is the first thing to keep in mind. We start with particles, we melt them, and we get a solid at the end of that. And we also have some vaporization. So the first physics is that you're having all this phase change from powder to liquid back to a solid with some vaporization. The second thing that we're seeing is that we have a powder that is loosely packed, and now we're going to make a solid part from it that is going to solidify from a liquid. So we have strong shrinkage stresses, both from the differences in compaction as well as the sheer thermal nature of going from a liquid and solidifying that liquid. We have a lot of complex heat transfer going on. All three modes, conduction, convection, radiation, are in operation. And finally, based on whatever is happening here, we get a structure that is evolving as this laser beam goes across. So this is a complex physics problem. There were like another 8 or 9 things that I hid, because but that is because I didn't want to talk to them, but there are other effects going on as well, but this is sort of like the vapor interacting with the laser, for example. Yes?
Are there any issues with contaminants?
Yes, I mean, is the short answer, but these machines now are designed with highly optimized fluid flow to clear out the plasma. So I guess I should take a step back. There are 3 sources of contaminants, at least. One is the powder itself that you get in, and further and this is a great question because I'm not going to address it, so I'll spend a couple of minutes now talking about it. But the first source is the powder. As it's received commercially from the supplier, I don't know about a lot of data showing that it comes in with contamination. The problem after that is that we start to recycle the powder. We want to recycle it to keep it affordable. The majority of our build chamber, and you'll see this, is essentially powder, with the part occupying 20–30% of that volume. So to say, we can't afford to toss out 60–70, so we go through this recycling process. And people have shown in the literature that up to 30 times, 17 or 18 in the literature, an OEM showed up to 30 times, they've been able to recycle the powder. So, but it's something to keep in mind. You have to follow the right procedures. So your powder is one source of contamination. The second one is the evaporation that does generate visible soot that you can actually see. There's a lot of CFD done, computational fluid dynamics done, to optimize that vaporization effect and carry it away from the incoming beam as well as from the material around it, so we don't have backscatter. But every time I run a build and I'm done with the build, I take a cloth and I just clean it, and I'll pick up so much soot on the top surfaces. After every build, we have to do that. So housekeeping is crucial, and there's no way, I don't have a lot of data on how significant it is with and without. And finally, the third component is the actual chamber itself and how well it is maintained, which is sort of, soot is one contributor to it, but contaminants from a previous build, maybe you ran Inconel and now you're switching out to stainless steel. So changing hoses, changing the gloves every time you switch from powder to powder. So that is a big challenge as well. And we have a tiny machine, as you will see, and for us, the switch out from one material to another is on the order of 2 to 3 hours, I would say. For the larger machines, it can be a day just to set it up. NASA might have 2 or 3 days to qualify, do some kind of evaluations before they change out. And that's why most people dedicate systems to a particular powder and don't want to change it. But broadly speaking, those are the 3 sources. But great question. And one of the big, to that gentleman's question about the properties, the big advance that happened from a physics standpoint was being able to melt the powder as opposed to just sintering particles together. That was the big step change that happened in this technology. And this is one example of a simulation where we want something like this, too much power. You can actually get these balls. It's called balling to form. But really what you want is you form a melt pool, and you're literally steering that melt pool everywhere you want a part on that layer. So it has to look something like this in the best case scenario. But it is a liquid, and there's all this turbulence and flow, convective flow effects that these people are studying. And what you typically, if you just take your laser and draw a line with the laser, this is, and cross-section it, this is sort of what you see. You see these very tiny grains form because you have very quick solidification. So you don't have a lot of time for large grains to form, and this is a result of that rapid solidification. So a lot of interesting physics is going on, but the key thing to take away is that we are fully melting this powder, and we have to if we're going to get fully dense parts. This is a quick video which, in the interest of time, I'm going to skip over. It's on YouTube, and no point seeing it. I thought it would be nice, but you're going to see the machine anyway, so we'll skip through that. Unless you all want to watch it. It's 3 minutes long. I'll take a vote. 1, no, no, okay, no, okay, wow. So we'll skip to that. It's if you search concept laser M2 on YouTube, anyway, I'm sure nobody's going to do that. But I spoke of materials being versatile with the laser system, and this is an example of what is possible today. This is what is commercially available. It's a subset of what people have demonstrated in R&D labs. Copper being one of the more recent ones that a lot of people are starting to show. They're able to do nickel titanium, also a more recent one. But what is commercially available, you walk up to the company and you say, I want to buy this. They sell you the powder. They give you the parameters that you operate your laser at. You will get parts that perform at close to forged properties, and I'll show you that in a minute. So these are qualified materials, qualified powders, qualified laser parameters, and the expectation is that you can go into production with these. There are obviously other kinds of problems, but that is the idea. We have stainless steels. Today we are set up for 316L stainless steel. That's what you will see when you go there. We also have hot work steels. We have Inconels, nickel-based alloys, both 718, 625, bronze, and even biocompatible cobalt chrome, which is very popular in the dental industry, who are big users in Europe of the exact machine we're going to see, because it's a really tiny machine, so the jewelry guys and the dental guys love that machine a lot. These are the so-called non-reactive metal alloys, but on the other hand, we have the reactive metal alloys, and those are typically aluminum and titanium alloys. And the reason this separation is important is because because of the reactivity of the particular alloy in question. In other words, how prone is it to catching on fire? This is a huge separation for a company like us, or for any university or anybody that wants to get into this area. There is almost, in terms of time, there is almost a 10-fold increase in what you need to do to work with reactive metals, the kind of protective equipment you need to wear, the ESD requirements, how you get rid of the materials back into the stream, how you clean filters. There are examples of some of these materials catching fire without an ignition source, just from a static spark. So that's why this separation is important. And it does increase the burden, and many suppliers, like including Concept Laser, who are the machine that we have, actually will sell machines that only do non-reactive because they want to, at a lower price point, because a lot of folks will only run non-reactive metals, especially the jewelry and some of the dental folks. But if you want to get into aerospace, if you want to get into biomedical implants, you need to sort of think about moving into this domain. So these are the materials, and I don't think I'm not going to spend too much time on this slide. But this is the machine that we're going to see in the middle, and this is only Concept Laser. It's more of a sales marketing slide than anything else. But I want to make a couple of points that this is sort of the range of slides that you're looking at, sizes that you're looking at, 3.5 inches, which is quite a shock for most people. that's the size that we have over here. It can do a lot, but obviously it can't do big parts. The next step up is 10 inches, and the largest metal powder bed-based metal system is this X-Line 2000R. That's 31 inches by 16 inches by 20 inches, and you're looking at about $2 million for this guy, about 200K for the low end. So just to give you a sense of sizes and price points, if you want to start saving up. And that's just that's the machine. You know, you need to set up your room in accordance with fire marshal requirements, oxygen sensors. You'll see a lot of that, fire extinguishers, walls, etc. So you can add another 20% to the cost to get your room ready, as a rule of thumb. So that's sort of the machine options. Application sectors, this is, again, a bunch of marketing stuff. Let me move into the properties. Since we have about, well, actually, we have 40 minutes, but we have to vacate this place by around 4:15, I think, at top. So if we go a little over, I hope you won't mind. I did not time this. So let's talk about properties. What kind of parts do we get? The first question is purely geometric before we get into the mechanical aspects. And that's why I'm calling it, I don't think that's a good word, but I mean not the mechanical properties, but the geometry. What does the part look like? So keep in mind the spot is 50 microns or 2 thou in diameter. Our layer thickness is between 20 and 30 microns. Today we're set up for 25 microns with stainless steel. That's something the supplier will tell you. You buy stainless steel, run it at 25 microns. We've got the best results with that. Use these parameter sets. So it takes away some of the, anyway. So a point that I want to make is that depending on what layer thickness you choose, you're typically going to get a feature like this, a thin wall, on the order of a couple of 100 microns. This is the smallest you can resolve. Anything smaller, you won't get good features. You'll get gaps and pauses in your feature. Maybe you can make a pin, but you can't make a wall because it will distort. So the rule of thumb from users in the real world, which is one of them is Proto Labs, not us because we don't operate in large volumes, but their data and what they spec to their customers is we could make parts that go down to 150 microns in feature size, typical. If you're making a thin wall, it'll be a function of how tall you make it because there are stresses in that part. And typically, we're talking about 3,000th of an inch plus or minus, and then an additional thou per inch. And I mean, this is only useful if you are in that business. A lot of times, we will get even better by post-processing and finishing off mating surfaces, holding certain dimensions, and running them on a CNC mill or a lathe, and getting that even tighter. But that is typically what is committed to the customer by Proto Labs, who use the same machine that we have and some larger versions of that same machine, concept laser machines. Surface roughness is one ding for this technology. Well, at least as it comes out, it is very rough. You will see some parts. After that, you can do a bunch of finishing, bead blasting, and other operations. You can even get jewelry grade surface finish. But as it comes out, so this is here the acronym SLM is used, but this is the surface roughness, and if you compare it to an NC turning or a milling process, it's about 2 times the roughness. Yes?
So you have feature minimum is 6 thousandths, plus or minus 3. What about a wall thickness? So what would be, I mean, I wouldn't imagine that you could have a 6 thousandths wall.
The minimum that you can make, and this is from a paper, and I didn't touch upon that, is people have shown 250 microns is the minimum you can make for walls that are not very tall. Proto Labs likes to quote a 1:40 ratio in their aspect ratios of how tall you make a wall. So you have if you keep that calculation in mind, then you can achieve 250 microns at a minimum, and then that will scale as your wall gets taller.
Okay.
Yeah.
Does the first layer have to be adhered to the bottom plate?
Yes.
Okay.
Yeah, and the reason I pause is because I did not start the build because I want to show you what we do on the first layer. We do something that's like a pre-treat where we have some powder. I'll show it to you, but that's a very good question. The first layer is the layer that is connecting the powder to the build plate, and if we don't get that right, we essentially are printing in air. So what we do is we run a lower power setting on the first few layers, and we repeat that. We do it 4 or 5 times just to get it's like a treating of the surface and getting the first few particles melted on top of it, and then we'll come with our first layer and build up from there. But the powder, thereafter we're fine, we just do 25 microns at a time, but the first layer we have to do that step. Yeah, great question, and I will see that when we go back. Yes?
What is the fair design, how to define the fair design?
What is the datum, the baseline?
They have defined only on the fair design part. How do you define is fair design?
Okay. So for surface roughness, we measure it on the part. But you're talking about the dimensions, right? When I say plus or minus 0.3, it is in relation to what? Is that your question?
Yeah, that's fair design. How do you define it?
He means like not a
okay.
wall that's at an angle, but like that.
Okay. This is, if you're referring to the fact that these numbers might vary depending on where you're measuring it, is it, for example, surface roughness is known to be rougher on a down-facing layer and less rough on a top-facing layer. So is that your question? Yeah. Let's talk later. Yeah. I mean it. I'm here till 9 o'clock, so let us really talk later. Yeah. 9:15. Somebody has to clean up too. But so that was dimensional. If we move one layer deeper, and by the way, for time, we still have 10-15 minutes to go. So if you're thinking, or if you have somewhere else to go, it's almost 4 o'clock was my point. Density-wise, this I've already said this. You know that this shows the density of the part. In other words, how much void do we have in the part, and you know, this is showing it as a function of how much energy you dump into it. And at some particular point, you get to an optimum. People have quoted in the literature 99.9% density, especially on titanium alloys. And if you keep adding more and more laser energy, you retain that density, but you start to see that other balling effect where you introduce additional surface roughness. But that was the big breakthrough. We can now get parts that have no voids compared to what we were doing before typically. And there's a whole history behind that, and fiber lasers and how they came up to speed. The second thing I already mentioned is the solidification grain structure. There is some structure to this. So this is the top view where the laser beam is scanning like this, and this is about as wide as this. And if you can actually make out, well, not me, but in this image you can make out the separation when you're looking from the top and the laser is scanning. You pick that up. And if you look at it from the side and you cross-section it, some people have shown, again, for titanium 6.4 with a laser-based system, they showed this kind of directionality to the grains and the way they appeared as bands if you took a cross-section. So that's just an observation. If we look at the mechanical properties arising from this, going back to that question, here is conventional forged. So you'd bring a piece of metal and you know, smack it till you got the piece that you want, and this is what people have shown with 3D printing, followed by a heat treat for tensile strength, for elastic modulus, for elongation at break, and for hardness. And this in the middle is the powder metallurgy, because it's sort of an apples to apples comparison. Both are starting with powders. This is using the conventional powder metallurgy process with something called as a hot isostatic press afterwards. So we've got 3 different processes, and 3D printing is very comparable for these mechanical properties that are listed over here. The one of the more interesting areas right now, so for the most part, for qualified materials, so that's the caveat. You like aluminums right now, we only get typically we only get one kind of aluminum, an AL MG10 SI. If you want aerospace grade aluminum, you're not going to get these properties, at least in the public domain, to the best of what I know. So if there is a qualified material, it is qualified against typically known material properties. So that's the caveat. I always tell everybody that yes, they have shown that they have good properties, but it is for these materials with that process. And this is growing, so this will improve over time. But at the moment, those materials that I showed before, we can expect equivalent properties for them. Finally, there are many open research topics, and I want to leave you with the notion that this is still an evolving field. So you have realistic expectations that what you see at the end and the parts you will see in that room and that you see in the media, there are still some real issues. Some of them have to do with fundamental understanding. That fatigue was one example, where how does the process influence the structure? How does the particles, how do the contaminants play a role in that? Why am I seeing trapped powder? How can I design better to exploit this technology? Lots of open questions around standards. If people come to me and they say, I want stainless steel 316L, and I will say, great, but how can you make sure that I'm meeting a certain specification in terms of its performance, mechanical performance, or typically with materials we have standards. The community is still working to generate these standards for these materials. We don't have very good material models to incorporate in simulation, so we can start to use simulation to predict performance of this. This is a favorite area of ours, and the one that we have some funding in is over there. How do we exploit the cost, and how do we do that cost benefit analysis? So when we want to scale, when we want to go to production, how do we ensure quality and we automate this? We have in situ monitors, lots of research going on, and safety is huge in this area, and nobody likes to talk about it much because it's a pain, but there are many of these technologies, and what is going into the air, be it polymeric, and how do you train for that? How do you set up for that? Where is the data for that? I'll show you the respirator I wear. Is it working? So I hope so. So there are still some open issues, especially when we're dealing with powders, or on the other end, we're dealing with polymers that have some vaporized effect. So there are some safety issues in this technology that still need to get sorted out, especially as we ramp into production. There's lots of post-processing involved. I'll give you some sense of this today. When the part comes out of the metal printer, I have to get in with a glove and a brush and brush off all the powder like an archaeologist. I have to then put the part in an ultrasonic cleaner, get out any powder that I was not able to remove with the brush. I then put it in a furnace, which is an inert gas furnace to relieve some of the stresses I spoke about, that solidification shrinkage. So for steel, I'll go to 550C, 800 or 1000 for Inconels, and so on. And then when the part comes out, it's on this build plate, and it has these supports. So I then need to get these supports out and saw them off. I can use different ways to do that, and then I have to use some hand tools to break off these supports manually. And then finally I have to do some finishing. You may not like the surface finish, and you will see some unfinished and finished parts. So I might do what we call micro peening or sand blasting. I might want to use a grinder, sander, wire. So there's still some artistic component at the back end of this. So a lot of work needed post-processing. The rule of thumb people quote is that material cost is half of the total cost. You can double that, and that's all my post-processing cost. Or the other joke is it takes for large aerospace companies, it takes 3 days to print a part and 30 days or 3 months to finish it. And I haven't spoken about inspection, I haven't spoken about machining, true parts. So there's a lot of back-end work that the part's not printed and ready to go, unfortunately. And I touched upon safety, but there's all these other things you will see in the room. You have to prepare a build plate each time. It has to have a certain surface roughness for that first layer. to form very well. So you mill it down, you bead blast it. In some materials you need to demagnetize it. We have very special vacuums that have water columns in them to isolate the powder. We run on inert gases, so we need to have O2 sensors. We have, this is what I typically wear when I'm cleaning the machine, and we need to have a special fire extinguisher for metal fires. We have sieves that recycle the powder, ultrasonic sieves, and you'll see that there as well. We need special cabinets to store these materials. So this is sort of that overhead that you have not seen in that sticker price that suppliers will show you. Safety and environmental considerations, there are 3 ways you can do damage. Laser exposure is probably the lowest one in terms of risk because it's a contained apparatus. But fire and explosion are very real, especially with the reactive metals, the aluminums and the titaniums. There are also some lesser known about physiological things like metal powder inhalation, and inert gas asphyxiation is well known, which is why you need the O2 sensors. You know, if you're thinking about getting a metal machine, this is sort of the 4 groups of people you have to work with. One is somebody to certify your equipment, which is a nationally registered testing laboratory, UL, the UL stamp that we see on everything. I know, he's like, really? I mean, come on. I just want buildings, this is all metal specific, okay? So it's not really for polymers. This is all around metals primarily. Building safety, you're going to connect into these 230 volt electricals. You're going to have nitrogen lines running in. Fire marshals, and finally environmental. You're going to generate this powder. When I clean the soot, I have paper towels with powder on them. I have liquid in my vacuum. Water with powder in it. I can't pour this down the drain. I have to have somebody come pick it up. For a small shop like us, it's about 150, 200 bucks a month for that pickup for just one tiny machine and one guy running it. And that's just for the city of Tempe. Every city may have their own requirements, but this is typical. So you get to know these 4 people in your city. And much more than you want to. Lastly, the software. Lots of software involved in this in additive, especially for metal. So the first one is what I call basic requirements. So you want to have something to design your part, CAD, right? SolidWorks, Autodesk, Space Claim, so on. The second one is you need something to take that CAD file that you now have and prepare it for your machine. And in the previous pictures you saw some supports. Who is designing that support? That's typically another software that takes in your CAD file and now adds supports, allows you to modify them. We use Magix to do that, but there are other options. Thirdly, you may need to repair the files you generate, either because they've come from a scan or when converting to an STL you've had some problems. This is not typical. But if you're doing a lot of scanning, a lot of reverse engineering, you'll see our scanner, you get files that need some repair. So you'll meet a guy called Demola. He'll tell you how he does geometry repair using DesignX, but not needed for most companies that are not going to do a lot of scanning. If you're an aerospace company, you want to know how this part is going to perform on your plane or whatever condition you're putting it in, or even in the medical field. For that, you can use analysis to really exploit that design for analysis. These are simple design modelers that allow you to create geometries, but are not solving that geometry for a problem. I'm not minimizing weight for a certain, I don't have any constraints apart from what I'm looking at as a designer. So I bring in analysis. There are these softwares that do topology optimization, softwares that generate lattices, lattice structures. You'll see a lot of those on the trip. And finally, softwares that do more conventional part analysis, that once you have your part, assuming you know how that material behaves, you can predict how it will perform in the field. So ANSYS, Abacus, finite element software sort of fall in this domain, though solvers of FEA solvers are used by topology optimization and lattice generation software as well. And finally, process R&D. If you want to truly understand why am I seeing that void, why am I trapping a particle, how can I change my laser fluence or my spot size or my energy distribution in that spot, you need to dig into process simulation. The aerospace industry, because they build such large parts, are really concerned with building parts that then distort because they have such large residual stresses. So there is a software called pan computing, another one called 3D sim. This is the suite they sell that will predict the residual stresses and the distortion you can expect in your part, so you can correct for that in your design, and then the final part you get, or at least that's how it's supposed to work. It's still a little in R&D, but the point is, as you go up the ladder, you have to bring in more software. And just to give you an example of cost, a Magix one seat is 20 grand and 5,000 or 3,000 a year for renewing it. So these softwares are so specialized in many cases for 3D printing, for metal, that they have higher price points. So you do need to think about software depending on what you're trying to do. Finally, this is my last slide, or last part, so 3 slides in this one, and then we are done. We do have an additive manufacturing ecosystem. Lots of companies in the valley are doing 3D printing. Got some of the big aerospace, aviation, and defense companies that are doing it locally. I don't want to call out anyone, but we do have some folks from Orbital here, and anyway, so but we do have lots of people coming here as well. My point is, aerospace is easily the largest driver of additive, and more so in Arizona and locally. So we are thankful to have them push this technology and drive a lot of us smaller companies that are supporting them. And this is a sort of a, just a list of small companies. I mentioned us, but there's also Titan that we really like working with, and they're very instrumental in pulling everyone together. You may not know that ASU Polytechnic campus in Mesa has $2 million worth of additive technology, metals as well. They have the machine we have and a larger machine, so very jealous of them. But they are, at the moment, they are the largest in terms of investment and equipment space university for additive in the Southwest region. That includes Southern California. So we really have a good R&D community. The UFA is doing some really cool work also with bioprinting in additive field, and also doing some electronics work with Raytheon in terms of combining 3D printing and electronics. So what we in June of this year, we started a manufacturing committee, and this is my plug for that committee. It's called the Arizona Additive Manufacturing Committee, AZAMC, and it's under the aegis of the Arizona Tech Council. If you know them, they are the ones that organize this and lead the effort in terms of setting up the meetings and all. But it's really us engineers that decide what we're going to talk about. And our main mission is to sort of open the doors to each other and show each other what we have, and teach each other what we learn with what we use. Influence local regulation. State senator, I don't know, but a senator often comes to our meetings or sends some aides because they're very interested to see what we can do. And we have lots of people that are on some committee or some standards committee, especially the Titan guys, that sort of feed back to us and tell us what is going on. And finally, the one that I like the most, which is why they put it at the bottom, is that we can group together to write research proposals or pitch for some ideas and get funding, SBIRs or university STTRs, and sort of, just because we meet each other once a month, we at least have that opportunity. We're about 45 entities now, so if you're interested in this, the only thing we ask is that you have an interest in additive, or you have access to a machine, or you want to get access to a machine, and that you can add value along these 4 regimes, be it K through 12 or research or anything at that level. So you can contact me, or you can contact the Arizona Tech Council if you know them, and we'd love to have you on board. So with that, I'd like to